The Michaelis-Menten mechanism is a mechanism for modeling this type of simple reaction where you have a single substrate and an enzyme, and they form an enzyme-substrate complex, and that goes on to form product. And we say that this forms with rate constant K1. The complex falls apart with rate constant K1 prime, and it goes forward to product with rate constant K2. And this model does work fairly well for a number of systems. Note that it is a model though, and so in many systems this model won't fit. So for instance, there are some systems where this last step here is not irreversible, so we get some back reaction. I should also note that this is enzyme catalyzed reaction, so we have to generate our free enzyme back at the end. Okay, so let's go ahead and analyze these kinetics. Well, we can see the speed of the reaction in terms of the product production here just can be given by K2 times the concentration of enzyme substrate complex. We have to figure out a way to express that in terms of the concentrations of our reagents, our enzyme and our substrate. Well, it turns out that in many cases, this K2 step, the second step, is fairly rapid, especially since when compared to the first step. And that often happens because the concentration of enzyme is relatively low. Okay, so in that case, what we find is the concentration of enzyme substrate complex is going to be fairly low. In other words, we're going to make this steady state assumption. And if you were to graph these three enzyme substrate complex concentration versus time, you'd find out that this is in many cases fairly low and constant throughout the time course of the reaction. So if we make the steady state assumption, it is that the change in concentration of enzyme substrate complex with respect to time is approximately 0. But now we can write an expression for this change. So what makes enzyme substrate complex? Well, only one step, right? That's the K1 step. So the K1 step times the concentration of enzyme times the concentration of substrate. That's going to produce the substrate, enzyme substrate complex, but then we can lose it in two other ways. We can have a backward step where the enzyme substrate complex just falls apart. We can also go forward to form product. Either one of those decreases the concentration of enzyme substrate complex. Okay, now there is a problem with this expression here, and that is that this is not actually a concentration that you determine when you set up the reaction. What you determine when you set up the reaction is the total concentration of enzyme. But of course that gets split between free enzyme and bound enzyme. So let's go ahead and label this as a concentration of enzyme total. That's the amount that you actually put into your reaction mixture, is equal to the concentration of enzyme free plus concentration of enzyme substrate complex. So free plus bound equals the total amount. Let's substitute that expression for ES, in other words E naught minus E, in here. So we get K1 times E total minus ES. That's equal to the concentration of free enzyme. That times the concentration of substrate minus K1 prime minus K2. That's enzyme substrate complex here. Times enzyme substrate complex. Great. So now what we can do is realize that we have only one unknown. The only unknown here, since we know how much substrate we're putting in and we know how much enzyme we're putting in. And I should actually point out here that the total concentration of substrate, we could write the same equation, right, is equal to free substrate plus enzyme substrate complex. In general, though, this is much, much bigger than this. And so typically what we'll do is say that these are approximately equal. Okay. Especially, normally we're going to be doing this as initial rates. And so initially, of course, the concentration of substrate is equal to the total concentration of substrate. Okay. All right, so we can solve this for the concentration of enzyme substrate complex. So first we have to do is gather all the enzyme substrate terms on one side. So if we separate the terms that don't have enzyme substrate complex, we have K1 times substrate times concentration of total concentration of enzyme. On the other side we have K1 times substrate times enzyme substrate complex plus K2 times enzyme substrate complex plus K1 prime times enzyme substrate complex. And so we can just gather all the terms together, pull out the concentration of enzyme substrate complex, get K1 times S plus K2, plus K1 prime. And all that is just equal to K1 times substrate times total concentration of enzyme. So if we solve for ES, get ES, it's just going to be K1 substrate total enzyme concentration divided by, so you've got this K2 plus K1 prime term, and we've got this K1 times substrate term. Now since we've got K1 in one place, let's go ahead and divide the top and bottom by K1, and we get substrate total enzyme concentration and a collection of constants, K2, K1 prime, all over K1. Plus concentration of substrate. And all that's equal to enzyme substrate complex concentration. Remember, the speed of the reaction is just going to be K2 times our enzyme substrate concentration. So it's K2 times this whole expression. So we end up with K2 substrate total concentration of enzyme all over, and we're going to call this whole collection of constants Km, big Km. So we have Km plus S, and this is the expression that you're used to for Michaelis-Menten mechanism. And we can abbreviate even more if we define Vmax is equal to K2 times the concentration of total concentration of enzyme. If we make that definition, then we can write V is equal to Vmax times substrate all over Km plus substrate. Okay, so let's unpack what this means. Let's write our definitions over here. We said Vmax is equal to K2 times total concentration of enzyme. Let's see if that makes sense. Well, if we were to plot the rate versus the concentration of substrate, and just to make clear, we're talking about initial rates here, right? So we could do this all, we could, if we wanted to, we could just do initial rates and initial concentrations. Okay, so we do a bunch of different experiments at a bunch of different initial concentrations of substrate, and what we see is if we have very, very small concentrations of substrate here, this term is not going to matter very much compared to Km. And V is going to be directly proportional to the concentration of substrate, so it's going to be linear. So imagine this as being a straight line. But this is going to get bigger and bigger, and eventually this will be bigger than K. And at that point, we can see that these were going to cancel out, and it's going to asymptote out with V equaling to Vmax. So we can put Vmax up here. So we know this has to asymptote like that. So that's the way the rate would vary with concentration of substrate. Now, Km, we said was K2 plus K1 prime all over K1. Or another way of saying this is that this is the off rate, right? Because this is decomposing back to form reactants, and this is going forward to form products. So both of those are decomposition of our substrate, enzyme substrate complex. Over here, we have the on rate. So you could think of it as off over on. So it's kind of like a dissociation constant, right? And so basically, if we have a small Km, it means the on rate's bigger than the off rate. That's going to be tight binding, right? It really has a high affinity for the enzyme has a high affinity for the substrate. And the converse is true. If you have a big Km, that means the binding, it doesn't bind the substrate very well.